to the module 2 of real analysis. In module 1, we have discussed the preliminaries of real numbers and some of the properties of real numbers like algebraic properties, order properties, density theorem of rationals and so on. Then later on we discussed what are intervals and what are nested interval properties, and based on that we were able to prove that the set of all real numbers is uncountable, and we were also able to establish that the set of all real numbers becomes a complete ordered field. Now we are in a stage to look forward to more complex topics in analysis, where we can define something called sequences of real numbers and series of real numbers, and we can see how that number pattern of sequences goes and where is it going to and so on. So, let us first move on to the definition of sequences. The sequence of real numbers is a function from the set of all natural numbers n onto the set of all real numbers. So, that means a sequence of real numbers can be considered as a function defined on the set of all natural numbers. So, the domain is the set of all natural numbers and the range is the set of all real numbers. Usually a sequence is denoted in single brackets, and we can see an example. We have a sequence xn which is equal to the sequence x1, x2, x3 and so on. So, this is the usual notation for a sequence of real numbers, because we can consider this as a function from the set of all natural numbers n to this sequence xn, which is a subset of R, and 1 is mapped to x1, 2 is mapped to x2 and so on. So, that is why we treat this as a function from the set of all natural numbers to the set of all real numbers, and it is usually denoted inside the single brackets. This is the usual notation for sequence xn. Now, we can move on to some of the examples. Let us see the first example, minus 1 power n. So, negative 1 power n is a sequence. Negative 1 power n is a sequence because if n is equal to 1, we get the image as negative 1. For n equal to 2, we get the number as negative 1 the whole square, which is equal to 1. For n equal to 3, again we are getting negative 1. For n equal to 4, we are getting 1 and so on. So, this is actually a sequence which consists of only two elements, alternatively negative 1 and 1. So, for all the natural numbers, we get either negative 1 as the image or 1 as the image, and precisely negative 1 is for odd natural numbers and 1 corresponds to even natural numbers. So, this is a very good example of a sequence. The next example that we have is sequence n, which is the set of all natural numbers itself, because this can be expanded as the sequence 1, 2, 3 and so on. So, this is also another notation for writing sequences. In some textbooks we can see like this as well, like we have said, in single brackets or in double brackets you can represent a sequence. Now, a fundamental difference between a set and a sequence is that in a set the ordering of elements is not important. The elements can be arranged in any order, but whereas in the sequences the ordering of elements, that is corresponding to the first element, second element, third element, like that, the arrangement of the numbers is very important in the case of sequences. So, that is the fundamental difference between a set and a sequence. Now, the third example that we have is sequence 1 by n, where for n equal to 1, this corresponds to the element 1. For n equal to 2, it corresponds to the element 1 upon 2. N equal to 3 gives you 1 upon 3 and so on. So, this is the sequence 1 by n. Now, so we have seen 3 different examples. There are many more examples like even natural numbers, odd natural numbers, etc. can be considered as sequences. There are many different examples, we will come to it later. Now, another method of defining a sequence is called a recursive definition, in which the elements are specified, some of the elements will be specified and the remaining elements, say for example x n plus 1, will be expressed in terms of the previous terms. For example, we can see a Fibonacci series 1, 1, 2, 3, 5 and so on. So, the first element corresponds to 1, second element corresponds to 1, third is 2, fourth is 3, fifth is, like that it goes on. So, this has got a one-to-one correspondence with the set of all natural numbers. So, definitely this is a sequence which is called the Fibonacci sequence, which is a very famous sequence in mathematics. And we can see that this sequence can be recursively defined. x1 is equal to 1, x2 also is equal to 1, and having defined these two numbers, we can define the rest of the sequence using the formula xn plus 1 is equal to xn plus xn minus 1. So, that means if you put n equal to 2, you can see that if you put n equal to 2 in the formula xn plus 1 is equal to xn plus xn minus 1, you can put n equal to 2, you will be getting x3 is equal to x2 plus x1, and we are already given the values of x1 and x2. x1 is equal to 1 and x2 is equal to 1. So, we can get this as 2, which is exactly precisely what is our x3. Then if you put n equal to 4 or n equal to 3, what you will get? N equal to 3 first. So, n equal to 3 gives you x4 is equal to x3 plus x2. So, having found out what is x3 and we know what is x2, x2 was 1, and therefore, we will be getting this as 2 plus 1, which is equal to 3. Likewise, x5 is equal to x4 plus x3, which gives you 3 plus 2, which is equal to 5, which was exactly what we required in the sequence 1, 1, 2, 3, 5 and so on. So, next element will be definitely 8. Like that, we can have the Fibonacci sequence. So, such type of definitions of sequence is what is called a recursive definition. Recursive means repeating. We can use the same formula for getting different values of the sequence. Now, coming to the limit of a sequence. So, we have seen so many examples here, like we have seen in the case of Fibonacci sequence, we have seen another example 1, 1 by 2, 1 by 3 and so on. So, finally, what happens to this, or at the end, where is this going to? That is a question of importance. So, finally, what happens as n approaches infinity, where is the sequence heading to? So, that is a point that we have to find out. So, keeping that in mind, we have something called limit of a sequence. A sequence x is equal to xn in R is said to converge to an element x belonging to R if for every epsilon greater than 0, there exists a natural number k such that for all n greater than or equal to k, modulus of xn minus x is less than epsilon. So, looking at this definition, this won't be so clear. So, let us see some geometrical approach. We can see, suppose the sequence as we discussed is a mapping, is a function from the set of all natural numbers to a subset of R. So, it can be definitely represented using a graph, because a graph is a pictorial representation of a function. So, we have 1, 2, 3 and so on. So, we have exclusively on the right side the function is defined, because it is defined for the set of all natural numbers. So, the sequences, the elements corresponding to the sequence are scattered. Say for example, 1 by n, if you take the sequence, the elements corresponding to the sequence can be represented as points, say 1 here, 1 by 2, 1 by 3 and going on. So, from the picture itself, it is quite evident that after some particular number, say 1000 or 100 or whatever, this is approaching which value? Approaching the x-axis. So, x-axis means the value will be equal to 0. So, that is exactly what is defined in the concept of limit. A sequence xn is said to converge or tends to a particular value x belonging to R if for every epsilon greater than 0, after a particular number k, all the values are at a distance less than epsilon from x. We have seen what is the epsilon neighborhood in real numbers, real number system, and so xn lies in the epsilon neighborhood of x. So, that is what exactly is the definition of limit of a sequence. Now, after defining a sequence, we are in a position to check whether if the limit exists, whether it is unique or not. So, a sequence in R can have at most one limit. So, that is a very important result. The limit of a sequence, if it exists, must be unique. Let us see the proof of this result. Proof of uniqueness of limit. So, in order to prove that the limit is unique, as always we will take two limits. Suppose if possible, let us take x1 and x2 as the limits, be the limits of a sequence xn. Then, by the definition of limit, given an epsilon greater than 0, there exists some natural number k1, because we have taken two limits, we will be having two natural numbers, say k1 belonging to n, such that modulus of xn minus x1 is less than epsilon by 2 for n greater than or equal to k1. So, that can be considered as inequality number 1. This entire thing can be considered as inequality number 1, and also there exists some k2 belonging to the set of all natural numbers, such that modulus of xn minus x2 is less than epsilon by 2 for n greater than or equal to k2. So, this can be considered as inequality number 2 or condition number 2. Now, what does this mean? For some natural number k1, for all the terms of the series greater than k1, they are at an epsilon, they are in the epsilon neighborhood of x1, and for all the elements after k2, all the elements are in the epsilon neighborhood of or epsilon by 2 neighborhood of x2. So, taking into consideration all the values which are satisfied by these two conditions. That means taking the common points or common values of the xn's, we will be having some k equal to maximum of k1 and k2, so that for all xn greater than or equal to k, automatically xn will be greater than or equal to k1 as well as xn will be greater than or equal to k2. So, that means both the conditions will be satisfied for all the numbers n greater than or equal to, for all the numbers, sorry, it is not xn greater than or equal to k, it should be n greater than or equal to k. For every n greater than or equal to k, xn will be greater than or equal to, again I made a mistake here, it is x not xn, it should be n. So, for every n greater than or equal to k, n will be automatically greater than or equal to k1 and n will be greater than or equal to k2. Therefore, both 1 and 2 are satisfied simultaneously, are satisfied. Now, consider modulus of x1 minus x2. Now, we insert xn inside this. So, we have x1 minus xn plus xn minus x2, so that we can apply our triangle inequality that we have discussed in one of the previous classes. X1 minus xn plus modulus of xn minus x2, and because both these are satisfied, n is greater than or equal to k1 and n is greater than or equal to k2, these two are less than epsilon by 2. So, we will be having this is less than epsilon by 2 plus epsilon by 2, and that is nothing but epsilon. So, remember that we had started with what? Given an epsilon greater than 0, there exists a k1 and there exists a k2. So, what is this epsilon greater than 0 actually? It is an arbitrary positive number. So, we can have this condition. Therefore, modulus of x1 minus x2 we have proved this is less than epsilon, where epsilon was considered arbitrarily. Hence, we have modulus of x1 minus x2 to be less than epsilon for every epsilon greater than 0, and hence we have, by the result that we have already learned, if this is true for every epsilon greater than 0, that forces our A to be equal to 0. So, this is a similar condition to this one. Therefore, this forces our x1 minus x2 to be equal to 0. That means, x1 is equal to x2. So, we have proved that our limit, if it exists, is a unique one. So, that is the proof. Now, we can see some of the examples. The first question is, show that limit of 1 by n is equal to 0. So, we have seen in the graph itself the sequence 1 by n is going to 0, but we need a rigorous proof because we are learning analysis, we need a proof for everything. So, we can have limit of 1 by n is equal to 0. How can we prove? We need this sequence to satisfy the definition of limit, that is, given epsilon greater than 0, we should find some number k. This is our question, whether we could find this number k belonging to n such that modulus of 1 by n minus 0, that means it is same as 1 by n itself, because n is definitely greater than 0, and so 1 by n is strictly greater than 0, and for positive numbers modulus is same as the value itself. So, 1 by n should be less than epsilon for every n greater than or equal to k. So, if we could satisfactorily or if we could successfully find a number, natural number k corresponding to this epsilon such that this condition holds, definitely the limit is equal to 0 is proved. So, let us begin with epsilon greater than 0. Then this implies what? 1 by epsilon is greater than 0, because we have seen already in the definition of positive real numbers, if epsilon is positive, 1 by epsilon is always positive, otherwise 1 cannot be greater than 0. Therefore, by Archimedean property, we have seen Archimedean property that we have studied. For 1 by epsilon greater than 0, there exists some natural number n or some natural number k, we can say in particular, such that k is greater than 1 by epsilon. So, k is greater than 1 by epsilon means what? K greater than 1 by epsilon indicates that 1 upon k is less than epsilon. And if you take k plus 1 or k plus 2 or any higher number to the number k, we can see 1 by k plus 1 is less than 1 by k, 1 by k plus 2 is less than 1 by k, and so on. So, these are all less than epsilon. So, in other words, if we have this result 1 by k less than epsilon, automatically it follows that 1 by n is less than epsilon for every n higher than or equal to the number k, which was exactly what we required to prove. And hence, we have proved that the limit of 1 by n is equal to 0. Yes. Now, the next example is also a similar one, because we need to show that limit of 1 by n square plus 1 is equal to 0. We know that n is a natural number, and so 1 upon n square plus 1 means denominator is n square plus 1, and therefore, 1 by n square plus 1 is less than 1 by n square, and that is definitely less than 1 by n. And so, the same technique that we were adopting to prove that limit of 1 by n equal to 0 can be applied here as well, because if we could find this is less than epsilon, automatically this will be less than epsilon. So, we need to prove only this part, which we have already proved in the first case. So, automatically this one also is proved. So, that is the proof of the second one. Now, show that limit of 3n plus 2 by n plus 1 is equal to 3. That is also a similar one. We need to take the definition itself. We are given 3n plus 2 by n plus 1, and the limit is given to be 3. So, we take modulus of xn minus x, that is what we have taken here. This is exactly your modulus of xn minus x, which we were expecting to prove in the definition. So, if you take this modulus, this is equal to modulus of 3n plus 2 minus 3 into n plus 1 upon n plus 1, because we can take the LCM, and simplifying this we can see that this is minus 1 upon n plus 1, which is equal to modulus of 1 by n plus 1, or that is same as 1 by n plus 1. And again we can use the same trick, 1 by n plus 1 is strictly less than 1 by n. So, we could, if we could successfully find a k greater than 0 or k natural number such that 1 by k is less than epsilon, which can be solved using the Archimedean property and so on, we could establish that this is equal to 3. So, that is how we establish that the limit is equal to 3. Now, in the fourth example, it is a slightly different one. We are given the difference of two surds. We will call these two numbers as surds. The numbers which are in the square roots are called surds. So, we have to multiply first by the conjugate and then we have to do the thing. So, we can see that if we have square root of n plus 1 minus square root of n, and after multiplication with the conjugate, that is square root of n plus 1 plus root n, we will be having n plus 1 minus n upon square root of n plus 1 minus plus root n, which is equal to 1 upon square root of n plus 1 plus square root of n, which is less than 1 by square root of n. So, as we have seen in the case of 1 by n less than epsilon, here also we have to find a k using epsilon square. So, that is a slightly challenging one, but that is also a similar method. And this last one, limit of b power n is equal to 0 if 0 is less than b less than n. So, here if you closely examine, the n that occurs happens to be as a power. So, we have to first take it to the base. So, we need to apply logarithm in this case and then find the limit. So, in this class we have discussed what is a sequence of real numbers. We have seen the definition of sequence of real numbers, how to find the limit of a sequence of real numbers, and if the limit exists, we have established that the limit is always unique. So, that is all for today. Thank you.